Okay.
I'm very sorry, I forgot to start the recording.
Okay, anyway, there were only basics by now.
So Cornelia, you must
yes.
start from the beginning.
Oh, I can show the first slide. Oops, it doesn't want to go back. Okay. So no, this was. So for those that were late, the Lie algebra slide and the Lie algebra cohomology slide, and now we are in low degrees.
Cornelia, I think for the last statement on the previous slide on cohomologies, you need simply connected for G, right? Because the first cohomology group of G is the abelianization of pi1 of G. If G is compact, right?
Yeah.
So I guess you need simply connected and compact.
Connected. Okay. Not so sure, because what we do? We do here just a derivative on the.
I mean, just take G to be non-simply connected, then you know that the first cohomology of G is the abelianization of the first homotopy group.
For instance, if I take
so
G,
it clearly depends on the first homotopy group of G, H1, the RAM of G.
Yeah, this is clear.
But
because
the left-hand side doesn't know about the first homotopy group of G, right?
Yeah, because if you divide by a discrete subgroup, the Lie algebra doesn't change, but the topology changes, of course. Yeah. So.
Yeah, I mean, also if you just look at this statement, it seems to contradict this. I mean, this Lie functor, right? Gives you a correspondence between Lie algebras and simply connected Lie groups. I mean, the left-hand side doesn't know anything about pi1 of G, but the right-hand side knows about pi1 of G. So it should be simply connected, I think, for the statement to be correct.
Okay, thanks for the remark.
Not a big deal, but
yes, thank you. So now we for H1 of G, H1 of G vanishes if and only if G is perfect. So the Lie algebra generated by brackets is the whole Lie algebra G. H2 of G, it classifies central extensions by R, and if we take it with values in G module, then it classifies also extensions by more general extensions. So we will see the next slide is about this. And H3 of G classifies crossed modules over G, but this is not in my talk. So central extensions. So central extension is a Lie algebra surjection P from G tilde to G. And so G tilde is the central extension, such that the kernel is central. So it's called a central extension by Z, by the kernel. If we denote this by Z, the kernel, then we get an exact sequence Z G tilde G. So this is sometimes how we find how we write the central extensions. How do we get the two cocycles that classify them? So we take a linear splitting, and then with the defect of S to be a Lie algebra homomorphism is the cocycle. And vice versa, if we have a cocycle, we can define a central extension of G. Yes, one still has to check that if it is a co-boundary, then we get a trivial central extension. So we indeed have that H2 of G classifies central extensions. by or
just a small interruption. I mean, there is this result by Bas and Kranz that is probably worth mentioning, which explains a systematic assignment of slim L-infinity algebras, higher Lie algebras, to classes in higher cohomology groups. This was later supervised by Huerta and Bas, and kind of has a physical meaning. So there is a systematic way of explaining also the geometry behind the higher cohomology classes here. Yeah.
So one can go further with the next.
Yeah, it's Bas Kranz. I think it's 2000 something. It came pretty late.
Okay. Okay. Thanks.
But in the latter case, your cocycles take value in this kernel, yeah. So
yes.
Not R, no.
Not in R. It's in Z.
Yeah.
But it's here. Z is central, so it's just a trivial G module. So I don't consider here semi-direct products or abelian extensions, or so just simple central extensions. Because now we need. So I have some basic examples, the trivial one, of course, and then the Heisenberg algebra, which is a central extension of R2. So where C is the central term, and here the bracket of AB is the central element. And for finite dimensional semi-simple Lie algebras, so we have the Whitehead lemmas that ensure that both H1 and H2 are 0. So semi-simple Lie algebras are perfect, and they have no non-trivial central extensions. The universal central extension of G is an extension, I denote it here by Q, and the Lie algebra is G hat. So it has this universality property that for any other extension P, there is a unique Lie algebra homomorphism F from the arbitrary extension G tilde to our universal one, such that the diagram is commutative. And a universal one exists if and only if G is perfect. And the G hat, this Lie algebra universal central extension, has the property that H1 and H2 are both 0. And if the kernel of the universal one, I denote it again by zeta, is finite dimensional, then we can read the second Lie algebra cohomology as the dual. So, but we can do these things also in infinite dimensions, but in this case, we have also the topology. For instance, in the example that I wrote below, the Virasoro algebra, G is the Freshelli algebra of vector fields on the circle. And the bracket is given by, so the extension is given by the Virasoro cocycle, so, integral over the circle of F prime G double prime, which is continuous in both entries. So this is what we require. We require that all the cochains are continuous. And so I will denote it by the cohomology as H continuous of G. And then also the projection should be continuous, and we require also the existence of a linear split in the definition of the central extension. It's that split that enables us to associate two cocycles, the algebra two cocycles to extensions. And this is something that we will use if G is perfect and H2 finite dimensional, then we get there exists, the universal central extension exists. So as I said, our Lie algebras of vector fields are in the symplectic case, so we have the Lie algebra of symplectic vector fields and the ideal of Hamiltonian vector fields. So the
Cornelia,
symplectic,
I
yes.
have a stupid question about the previous transparency.
Yes.
So the perfectness condition is understood on the nose. So it's again, in this topological case, it's again equivalent to the commutant of G with itself be equal to G, or you need some completion there?
Okay. You might be right that one needs something.
I mean, I wonder if this works for any topological algebra, or you need some kind of complete topology, something like a
I don't know,
Frechet
we
topology.
will work with Frechet, and I don't know. Thank you for the question, but this is something I don't know how to answer now.
Okay, thanks.
What I can say is that if G is not perfect, then there are these so-called versal, not universal, so that we don't have unique. Next, we have just existence of of F. But so this is what I wanted. Actually, I should write down your questions so that I don't forget them. But maybe I will remember all of them.
Will you also consider integrated, well, sort of an integration of the short exact sequence representing the central extensions, like to the group level? I mean, the question is non-trivial. It was addressed by Tuinman and Wegenring, if I remember correctly, for H2. And of course, for H2 is already a little complicated, but then for higher cohomologies, it's really tricky. It leads to kind of gerbs.
Yes, so I was only interested in H2, but even in H2 is not simple. There is this work of Karl Hermann Neb about, there was a time where he worked on central extensions, abelian, even general extension, but what are the conditions, the obstruction to integration, and they lie in pi1 of the group, of the Lie group, and in pi2 of the Lie group in infinite dimensions. So pi2 is not necessarily 0, and there is this so-called period homomorphism, and for the pi1 we have the flux. But in this special case, we manage, but this is still work in progress, we managed to integrate the universal central extension, the one for the volume form, in to a universal Lie group extension, but only in dimension m equal 3, and we use gerbs in that setting. And but I decided not to enter into that complicated case, especially because it's not yet polished, but we are sure that it works in dimension 3, because in dimension 3 mu, yes, is a 3 form, and then we get the gerbs, and then one can take gerbs preserving diffeomorphism and so on, and one uses them to write the universal central extension.
But I think in these situations, there is a geometric interpretation of the quotient algebras.
The quotient between
modulo the derived ideal, yeah.
Can you say again, Janusz? I didn't got it, the question.
So you have symplectic vector fields and Hamiltonian. So you
yes.
quotient, yes.
The quotient is H1 de Rham, and in the second case,
Yeah. So
minus 1 de Rham. Yes, I should have.
this is what I'm saying.
Yes, thank you. What I wanted to stress here is that here, in general, the symplectic vector fields are not perfect, and the divergence-free vector fields, unless we have this vanishing of the de Rham cohomologies in degree 1 in the first case and degree m-1 in the second one.
So these results are require compactness of M or not?
With the when M is not compact, I wrote it for compact here. Actually, I wrote it for compact here because no, here we don't need compact. There is, for the same Hamiltonian case, we have also this Calabi homomorphism, which introduces a second. There are 3 levels in the derived Lie algebra for symplectic vector fields. For divergence-free vector fields, there are only 2 levels. But if M is non-compact and we take compactly supported, so it's a bit more intricate. But here, yes, but here, if we don't take compact support, then this is true for every M.
Okay.
Yes. Okay, so these are our objects. So the exact divergence-free here is just like the simplex, the Hamiltonian. Just so alpha we'll call is called the potential of the vector field x alpha. Stream function, stream vector field for when we are in fluids. So something that will appear in the symplectic case is the canonical homology. So this is the canonical homology in the case when M is symplectic. Here the last line is written if more general, if there is Poisson, then we have this delta differential that is given by contraction with the Poisson tensor, but by vector field. But here, in the symplectic case, we have concrete formulas which we needed in our computation. So we have the symplectic Hodge star that is defined similarly as the Riemannian star, but here the pairing between beta and alpha is done with omega. So here I gave the formula on these special types of K-forms. The canonical homology, the homology for the complex with the delta is star d star. This appears in Grilinski's paper 88, and again on these special K-forms, we see the bracket between the functions. The Poisson bracket appears in the formulas. And what is important for us is its relation with the de Rham cohomology. So the dual of the canonical homology is the de Rham cohomology. And these are the main results. So the conjectures of Roger. But he did formulate it with universal central extension. I remember more like about the Lie algebra cohomology, but it's almost the same up to the perfectness of the Lie algebras. So in the symplectic case, we have this, the central extension is 1 forms on the symplectic manifold modulo delta omega 2, so delta exact 1 forms. in the canonical homology complex. So the projection is associating the Hamiltonian vector fields to the Hamiltonian function delta alpha. And the bracket on the quotient, so I denoted alpha bar, an element one form modulo delta exact one forms. So it's of this type FDG. Delta alpha is a function, delta beta is a function. Yes, we checked it. So the algebra, it is perfect. It's H2 of it is 0, and we get the universal central extension. In some sense, the second result, it looks simpler. So here you see it's not so the central extension is m-2 forms modulo exact ones, and we already have the potential of the exact divergence free vector field. So it's Q of alpha, class of alpha is X alpha. You see, in the other case, we don't if we are given the Hamiltonian vector field, then the Hamiltonian function, then to extract alpha is the, yes, we need delta -1, so it is more delicate, which can be seen, or the requirement that m is greater equal 3 is necessary. Because m equal 2 behaves like the symplectic one. So only from 3. So we need enough space, at least 3 dimensions, to be able to work in the volume case. And we require this finite dimensionality of what will be the second Lie algebra cohomology group, so that we encountered before. Maybe I will recall it here. If G is perfect and of H2 is finite dimensional, then it implies that we have universal central extension.
How big is the center of this extension?
How big is this is what comes now. Thank you. So for the symplectic case, we have it here in the last line. The center is H1 canonical, which is the same as H2n -1 the RAM. See this? We can see it here because Q is basically delta, and so the kernel of Q is kernel of delta modulo image of delta, so it's H1, and the same is in the second one. So
okay,
is in the symplectic case, we automatically get that H2 for here for Hamiltonian vector fields is H1 the RAM, because H1 the RAM is the dual of H1 canonical. And one can realize, and this is actually what Roger was doing with these Roger cocycles. So as I said before, one has to extract the Hamiltonian function, and in order to write the Lie algebra 2 cocycle associated to a closed one form alpha. So if we take here in H1 the RAM the class of alpha, then the bijection is with the Roger cocycle, the class of the Roger cocycle psi alpha. And it works also for C infinity and for the Lie algebra for M symplectic.
But from this formula, Roger, it follows that if you remove f from the integral, this should be 0, yes?
Yes, it is, because you move the Hamiltonian vector field to the right, you get something exact, and because alpha is closed, then it's closed wedge exact,
Yeah.
and it's
Or compact, yeah, okay.
Yeah, so even if it's not compact,
Yeah,
we have...
which is not obvious from the first side, yeah. So.
Yes, you're right, you're right. We have results also in the non-compact case. We made them big table with, I had it on my slide, but then I removed it, unfortunately. But it is in our 2015 paper. So this is, for the Hamiltonian case, we have the Roger cocycle, and here we have the Lichnerovich cocycles for the divergence-free case. So these are associated to closed two forms. So we have a closed two form, and we insert the divergence-free vector fields. You see, this works also for divergence-free vector fields. We don't have to necessarily pass to exact ones. And we integrate with the volume form, and these are the algebra cocycles. And but if we want to compute the cohomology, we work with the exact ones. If we want the cohomology of the whole algebra of all divergence vector field, that there are some cocycles that are inherited from this quotient, which is the Ram cohomology group, and there we have this simple cocycles on something abelian. We pull it back, and so one can say something also about the whole Lie algebra.
Probably you can assume that eta is compactly supported and M need not to be compact then, yeah?
Exactly. We can work also in this, and actually...
So the version for non-compact manifold, yeah?
Yes, actually what we needed, because our proof works, is done first locally, so we consider M equal Rn, and then we need compactly supported vector fields, and then we glue them, and so but we use then, we extend to all the vector fields, because we use homogeneous vector fields in showing that, so if M is Rn here, actually H2 is 0, because Rn has no de Rham cohomology, and in showing this is 0, we really have to get our hands dirty, very dirty. Okay. The ingredients that we use in the proof, one of them is this Petry's theorem, which is that, so first, what does it mean for such an so if we have E and F vector bundles over M, and so this is what we need, sections of one vector bundle and the continuous dual of sections of the other vector bundle, because we will start with the two cocycle, and then we will do one cocycle out of it with values in G prime, from G to G prime. So this is the setting we will need. We call it support decreasing if really the support is shrinking. For
probably you assume linearity somewhere, yeah?
Yes, it's linear, of course. Yes. And Peter's theorem ensures that phi is locally a differential operator of finite order. Locally, it's a finite order, and this we will use in both cases, and we will use something like this perfectness trick. I try to write it so abstractly because we will use it on functions for the Hamiltonian case and for forms for n-2 forms in the volume case. So the idea is that by starting with a cocycle on G, but here G could be G hat or G the extension or even the Leibniz case, it also works, Leibniz algebra. And we induce the map, which is one cocycle from G to G prime. And this psi is support decreasing if so the two cocycle we can call it support decreasing if for alpha beta having disjoint supports psi of alpha beta is 0, because then if we go to psi hat, then we will get that psi hat is support decreasing, and we can apply Peter's theorem to psi hat. And now we will use, in order to show the support decreasing property, we use the perfectness. If alpha and beta have disjoint support, so this C means the complement of support of beta. So then alpha, we can write alpha as, by the perfectness, as a sum of brackets. And then by computing psi of alpha and beta, we use the Jacobi, the cocycle property of psi. And then we get these brackets, which for our, in our cases, where the bracket is either the Poisson bracket of functions or the bracket here on the, here, where is the Lie derivative x alpha beta. So if they have this joint support, then we get 0. So then this is this perfect that we called the perfectness trick that allows us to use Peter's theorem and then to really write concretely differential operator, and then we can work locally, and then we can glue them. And so this is the idea.
Excuse me, I have a question. In the other slide,
yes,
you have this function, this phi, big phi.
Yes.
You have such map only between section without having any map between the vector bundles. There's nothing induced by some.
In our case, yes. I don't know.
So it's
when it
well, for me
works.
strange. So you have a map between section without having no map between vector bundle. It's
This is a dual of sections.
Oh, yeah, no, you see, differential operators act on sections and not give maps on the level of vector bundles.
yes, but what is the role of this phi, big phi? It's I cannot see. It's
No, so as I understand, here
so
Cornelia wants to show that it is a differential operator.
okay, okay.
It's
So define phi by f in this way. Okay, so
it's a distribution valued operator, right? So you apply it on completely supported section, but you end up with something in the dual of completely supported sections of F. I mean,
but for another vector bundle.
so yeah, so that's why these AIs here are distributions.
Yeah,
So
these AI
distributed
distributions, yes.
Okay.
is
Yeah, so-
something that's very common, by the way, in quantum
Yeah.
field theory.
Yeah, so Peter's theorem says roughly that local operators are locally differential operators.
Okay.
Yes.
Okay.
Exactly.
Thank you.
So, in the for the first theory, so now for the symplectic case, so I will just it's really basically what I said before, but just to see on which spaces
I'm sorry,
we
maybe
apply.
you should keep in mind that you have at your disposal two parts, 45 minutes each. So if you think that this is the right moment to break up,
I think that I can finish in 10 minutes.
all right. I wasn't aware of that. Okay, then please.
And then yes. Oh, I didn't prepare for such a long. Yes. Okay, so I prepared it for 1 hour.
Fair enough.
So
Please,
how
then.
much time did I use by now?
45 minutes.
45. And if I use 10 more minutes?
Sure, you're free to go on. Yeah. I just wasn't aware of
okay.
how you want to go. Sure.
Thank you. So here is the two co-cycle on functions. So we showed it basically for the Poisson algebra of functions on a symplectic manifold, and then we have this psi hat from functions to distributions, and given by a two co-cycle. We start with an arbitrary one, and then we show it is diagonal, and so we use Petry's theorem. We write it as the derivation, and this step is the ugly one, where we show the derivation is of order 1. It's a calculation in local coordinates, and it's like a bootstrapping. I don't know. Rationament. I don't know. So, and then we can write it as a current distribution of on-forms applied to GDF. And then we use the fact that psi is a two co-cycle, and we see that the factors are functional, and then we see it is an delta of something, and GDF, delta of GDF is bracket F in G, and so we get the psi is trivial. I forgot to write this very last line. So this is the idea behind. And we were thinking, okay, let's apply the same for the divergence case. But there, we don't have, so we have let me go maybe back to, I should have put it here, the main results. So here, no, we have this m-2 forms, but so we could not apply directly Petry's theorem, but we could apply it for omega m-2. But this one is using this very same bracket, it is not, without dividing out the exact ones, it is a Leibniz algebra. By the way, in this case, omega 1 without dividing this out is not the Leibniz algebra. So we have this Leibniz algebra, the definition. So we have it's a non-commutative generalization of Lie algebras. Is the left Leibniz algebra is given by a bilinear map that satisfies this left Jacobi identity. Examples.
Excuse me, one remark.
Yes.
Here there is a very important the form of the Jacobi identity you use. If you use the form which is often you can often meet that they are cyclic permutation, that of course this is not true that this will define your Leibniz algebra. This identity simply means that the adjoint of the bracket is the commutator of adjoints, yeah, which has algebraic meaning.
Yes,
So,
or the adjoint is a derivation.
Yeah, so this is the right form of the Jacobi identity, not the cyclic permutation.
Yes, yes. Thank you. I'm glad I have the right form on the slide. Yes, it's. I was trying to even this simple one on R2 is a Leibniz algebra that is not a Lie algebra. We can recognize that it's not a Lie algebra when this ideal of squares. So the ideal generated by the squares, so here BB is A, so the ideal of squares is non-trivial. If we factor out by the ideal of squares, then we get the associated Lie algebra to a Leibniz algebra. So we show that this omega m minus 2 of m with this bracket is a Leibniz algebra. And we also show that the ideal of squares is given by the exact m minus 2 forms. And we show it is a perfect Leibniz algebra, so the same definition works also in the Leibniz. By the way, there is also the analog of Chevalier-Eilenberg homology. So we were also trying to classify the two cocycles for the Leibniz algebra, so it works similarly. From the theorem, then we automatically get that also the Lie algebra that is our candidate for a universal central extension is perfect, and the omega here is not here, should not be here. It's exact. It's perfect, sorry. So, and I said the ideal of squares is given by the exact m minus 2 forms. This was again proved by really working in coordinates. And then using this paving principle, I forgot his name, this Ostrand something, to get local finiteness, and so to patch them together. So the outline of theorem 2, and I'm almost done. Now G hat is this quotient. And then we have the Lie algebra that is the universal, the candidate for a universal central extension. We take a 2 cocycle, and then we have a map psi hat, and then we go to L. We pull it back to L, to the Leibniz algebra, because L has the property that it is it lives on on m minus 2 forms, which are sections of a vector bundle. So in order to avoid this quotient, we use the Leibniz algebra, and then we work on the Leibniz algebra, and then we can use Petry's theorem. We have a good local coordinate expression, it's a differential operator, and then surprisingly, representation theory of the of SLM comes into play. It's SLM because we are working with divergence free vector field, so the infinitesimally, so the derivative is in SLM. But then the proof goes inductively on degree of, so we will use polynomial vector fields, and then we use homogeneous of degree higher and higher, and then finally we find this local potential. Local potential means that we want to write psi as the Chevalier-Eilenberg differential of one cochain, and so this one cochains, then we glue them, and then we get that H2 of G hat is 0, so this will ensure that G hat is the universal central extension. And I wrote here again that our main theorem, and that's it. Here some of the references. Yes. Thank you very much for your attention and
Thank you
for listening to me.
Yeah, let's thank the speaker.
Thank you.
Any questions or comments? There have been quite a few along the way, but are there any further questions or comments?
If you can maybe tell us more about what's happening beneath this complicated proof. So in some sense, all your arguments are ultra-local, right? They are about differential operators.
Yes.
And all the rest is some kind of standard gluing, if I understand correctly. Like partitions of unity and things like that, I guess.
Yes, there is some sheaf theoretic. There is
I mean,
you
by this you just
use
mean
the
that
sheaf.
they are sheaves and they can be glued, right? In the standard
Yes,
sense.
it's the sheaf of currents of the continuous dual of n compactly supported n-2 forms. And there, yes, this is the gluing part.
So I could somehow separate your arguments into sort of a hard part, which is this ultra-local analysis, this operator theoretic analysis, where the action is going on, and some gluing, which is, I guess, not difficult, right? Is my understanding correct? So in some sense, the heart of what's going on here is this operator theoretic.
Yes. And we also use a kind of Poincaré lemma for differential operators, and we couldn't find it in the literature. So if we have this our psi hat, if it vanishes on exact form, so composition with D is 0, then it is of the form there is a differential operator such that psi hat is the D ring differential, the differential operator. So there is a kind of Poincaré lemma for differential operators which we couldn't find, so we will write it in appendix, I guess, in the paper. And yes, so
but these theorems have global characters anyhow. You cannot glue the RAM cohomology from local forms, yeah, because this is nonsense, because of the Poincaré lemma.
Yes. So it's why we have on for yes, if M is Rn, and we will take compactly supported, H2 is 0, and so all this will have no. This part is not my specialty. I have two co-authors, which fortunately they are better than me in this part. So the hard part is really, so this gluing is in the half a page, but the hard part is really to show it for Rn. So first we use Petry's theorem, this is, and then we use this Poincaré lemma for differential operators, and then is the induction result where so with induction on the degree of homogeneity. So we use the fact that K homogeneous vector fields bracket with L homogeneous vector fields are vector fields of homogeneity K plus L minus 1. And then we see that if yes, if K0 L is 1, then so it's we have an action, and so this will be in the first step we have this yes, the first in degree 0, then we use Poincaré lemma for currents, but with values in lambda m minus 2 Rn. So it's this the linear version of omega m minus 2. And then in step 1, we use the Whitehead lemma because we have SLN actions, and their H1 is 0, and we get the one cocycle. And then the next step, we use really irreducible representations of SLN, because then we have again the action on K of pure degree K vector fields, and then we get an intertwiner between two SLN representations, and then we see that it has to be actually vanish, and then so it's a bit intricate. And hopefully it will be this summer on the archive.
Okay. Thank you.
Thank you. Thank you for the question. For all the questions by now.
Thanks a lot. If there are no further questions, then let's thank Cornelia again. And that's all, folks, for this semester. We're very happy to have had you with us. I think we can count this semester as a successful one, and we'll be back after the summer break. So stay tuned. We'll announce the upcoming speakers sometime soon. So thanks a lot, and enjoy the summer.
Okay, thank you.
Okay. Have a nice
Bye-bye.
summer. Goodbye.